Okay, the next topic on this multiple integration is double integrals and volume. So now we should talk about double integrals and volume. So volume is just kind of a three-dimensional version of area, right? The same way we computed area, we can compute volume. So let's start from, let's see some explicit examples, okay? So there are different ways to kind of explicitly decide like how to express this thing. So I would start with an example. Suppose we have a region. So this is a three-dimensional space, X, Y, Z. Suppose we have a surface here, X squared plus 2y squared plus Z equals 4. Okay. This is a surface. If you remember, this is a paraboloid. Okay. If I look at this, surface, if I see how it looks like, this is gonna be something like this. It's gonna be something like this. I hope my graph makes sense. Maybe it's not very good. Maybe something like this. You see, it's a surface. Now I can look at this surface where Z is positive. It continues, right? It continues, goes down. I'm just looking at the positive side, the side where it's above 0. Z is above 0. And I want to compute the volume of the solid region, which is bounded by this plane, which is bounded by this surface and with XY plane. So look at this XY plane, look at this plane here. There is a plane there and there is the surface, right? There is some region inside. There is some region inside. I want to compute the volume of what I have inside. What is the volume? Okay, that's the question. Now, just like area, when I want to compute volume, just like area, which I took integral of 1, I should take integral of 1. For area, I had double integral. For volume, I have triple integral. So I have a triple integral, but okay, maybe it's better to go step by step. So I have triple integral. I would have dx, dy, and dz, and I should decide about what is like the values, what are the bounds for each of them? What are the bounds for x? What are the bounds for y? What are the bounds for z? Okay. So here, what can I say about, say, which one is better? What are the bounds for x? Can you find the bounds for x? I'm taking integral with respect to x first. So I should first find bounds for x, then bounds for y, then bounds for z. The point is that when I'm looking at my first variable, which is x, in the bounds for x, y and z are allowed. I might have y and z in them. When I look at the second variable, I'm done with x. In the bounds, there might be something in terms of z. It's okay if I have something in terms of z. When I look at the last variable, I'm done with x and y. I should have only constants there in as bounds of x, as bounds of z. Also, the order really doesn't matter. You can do it in any other order. So what are the bounds for x here? How can I find what are the bounds for x? Well, look at this thing. X squared, I want to find bounds for x, so I should try to isolate x. X squared is equal to 4 minus z minus 2y squared. So x is equal to plus or minus the square root of that. Okay, and actually x is between these two values. X is between square root of 4 minus z minus 2y squared and minus that thing. These are the bounds for x. What are the bounds for y? How can I find the bounds for y? Well, I mean, what I'm going to tell you is not always correct. It's not mathematically rigorous. But let's just, because, well, we also don't have a lot of time. The idea is that I would just give you a trick, which usually works. The idea is just to ignore the x in this function. Just ignore x. What would you get? You get 2y squared plus z equals 4. Therefore, y squared would be 4 minus z over 2. Y would be equal to plus or minus the square root of that. And those give bound for the integral. What are the bounds for z? Well, z starts at here. This is 0. It gets up to here, which is 4. So the bounds for z are 0 and 4. So we have the bounds now. So we should compute the integral with these bounds. So I should just write down these bounds here. For this one. And then the bounds for y. And the bounds for z. However, computing this integral might be extremely hard. There is no reason why we can really compute these integrals. These integrals can be very, very hard. And I think this one is. I don't think we can really compute this integral. So it's correct that volume is equal to that, but not easy to compute. So we need another way of computing the integral. We need a second way of computing the volumes. So this is really a formula for volumes, but it's very hard to compute that. So there is a second way to compute volume. The idea is that if I look at the surface, I can think about z as a function of f, as a function of x and y. So here z would be equal to 4 minus x squared minus 2y squared. Okay. A second formula for volume is a double integral, not a triple integral. And it's equal to double integral of f of x and y. Say dy dx. So there are two ways to compute volume. I can compute the volume by taking triple integral of 1 with, say, dx, dy, dz. That's one way. I can compute the volume with a double integral, but rather than taking integral of 1, taking integral of f of x and y. Or there are two ways to compute the volume. This one or this one. Sometimes one might be easier than the other one. We should use whichever which is easier. I mean, here, this one would be easier. So here we have the double integral of f of x and y dy dx. We should find bounds for y and x. The bounds are exactly what I told you. So the bounds here for y are here, the bounds for y. What are the bounds for y? Maybe I should ask you. Take a look and think for a few seconds. What are the bounds for y here? That's plus or minus 2. They are the bounds for x. So you see, first we are taking integral with respect to y, and then we are taking integral with respect to x. When we are taking integral with respect to y, there might be something in terms of x there. When we are taking integral with terms of x, there should be only constants. Okay, so when we want to find out what are the bounds, actually we should look at this region. This is the region we are taking integral over. There's an ellipse there, as you can see. And the equation of this ellipse here is x squared plus 2y squared equals 4. So if I isolate y here, I would get y is equal to plus or minus 4 minus x squared over 2. These are actually the bounds for y. This is how to get bounds for y. 4 minus x squared over 2 and minus 4 minus x squared over 2. And the bounds for x, well, I should just ignore y. If I ignore y, I would get 4 minus x squared. And if I set that to be equal to 0, 4 minus x squared to be equal to 0, I would get x is equal to plus or minus. So those would be the bounds for x. So the integral would be double integral of f of x and y, which is 4 minus x squared minus 2y squared, dy dx. Bounds for y are minus the square root of 4 minus x squared over 2 up to 4 minus x squared over 2. The bounds for x are minus 2 to 2. Now I should compute this integral. Well, that might not be really easy. Let me try. It's, well, let me try to explain it, because there is one more trick we need to learn, but I would explain that here. So first I should compute this integral. 4 minus x squared minus 2y squared dy from minus 4 minus x squared over 2 to 4 minus x squared over 2. Okay, integral of 4 is 4y. Integral of x squared is, again, x squared here is a constant, right? So when I take its integral, it would be just the constant times y. And then integral of 2y squared is 2 over 3y cubed. And then I should plug in these two numbers, 4 minus x squared over 2 and minus 4 minus x squared over 2. I should plug in these for y and then subtract them. And what I would end up with if I do that is, well, you should really do that. What is that? It would be, okay. So, so it would be 2 times 4 square root of 4 minus x squared over 2. Maybe there is not enough space there, actually. I can write it in the second line. So it would be 2 times 4 square root of 4 minus x squared over 2 minus x squared, 4 minus x squared over 2 minus 2 over 3 4 minus x squared over 2 cubed squared root of that. That's what we are going to get, which is quite complicated. But we can simplify this thing. So I can simplify it. So let's go to the second page. So we have 2 times 4 times the square root of 4 minus x squared over 2 minus x squared times 4 minus x squared over 2 minus 4 minus x squared over 2 cubed. And then there is a coefficient 2 over 3. Now this part is like integral of a cubed. Integral of a cubed, where this thing here is a, for example. A cubed can be written as a squared times a. There would be integral of a squared, integral of a. Integral of a squared is a, so it would be a integral of a. That the same thing happens here. So 4 minus x squared over 2 cubed, that thing, that comes out of integral. So we would get 2 times 4, integral of 4 minus x squared over 2 minus x squared, integral of 4 minus x squared over 2 minus 2 over 3 times 4 minus x squared over 2 integral of 4 minus x squared over 2. Okay, and then this 2 cancels with this 2. And then we can simplify things a little bit. So we have 4 times this integral. We have 4 here. And we have 4 times this thing here too. Or we have x squared. Here we have x squared too. We can simplify it a little. And what we would get is, we get 4 over 3 square root of 2. 4 minus x squared over 3 over 2. So this is what we will end up with if we simplify it. I would trust you can do that. That's a good exercise for you. So that would be the innermost integral. Now remember, we should take another integral with respect to x from minus 2 to 2 of what we got. 4 over 3 square root of 2 times 4 minus x squared to power 3 over 2. How can we compute this integral? Well, I mean, this is not an easy integral. Note that there is x squared, and then there is another power 3 over 2 there. So a good idea for this thing is change a variable. It's a little bit exhausting integral. It takes a lot of energy. So if we let x to be, let me think. If we let x to be sine of theta, this is the change of variable we should do. Usually when you see, or maybe 2 sine of theta. Yeah. Usually when we see like 4 minus x squared, 9 minus x squared, like 1 minus x squared, these kind of integrals, they suggest this change of variable would work. If I take it like that, this integral would change into integral of 4 over 3 square root of 2, 4 minus x squared, which would be 4 sine of theta squared to the power 3 over 2 dx. What is dx now? It's 2 cosine theta d theta. And then 4 minus 4 sine squared is 4 times 1 minus sine squared. But 1 minus sine squared is cosine squared, right? So I would get 4 over 3 over square root of 2, 4 cosine squared to the power 3 over 2. I can rather than over 2, I can just write radical times 2 cosine of theta d theta. Now, square root of 4 cosine is just 2 cosine of theta. And then there is another 2 cosine of theta there, d theta. If I multiply them, I would get 8 over 3 square root of 2 times 4 cosine theta squared d theta. Oh, sorry, there is a power 3 here. So it would be cosine cubed. Sorry, it would be, I made a, there's a typo here. So it's 2 cosine theta cubed. So here I would get, I would get cosine to the 4, actually. And the coefficient there is, if I understand correctly, it's 128, yeah. So here I should compute cosine to the 4. So that's another good integral. I would just write down the final answer. We have, so there is one thing to note here. If x is minus 2, theta is, what is theta if x is minus 2? Does anyone know what are the bounds? What would be theta if x is minus 2? So if x is minus 2, 2 sine theta would be minus 2, right? If 2 sine theta is minus 2, sine theta would be minus 1. What is the theta which gives us minus 1? You're close, but not exactly. It's minus pi over 2. And when sine theta is 2, it means sine theta is 1. It means theta is pi over 2. So this integral is from minus pi over 2 to pi over 2. And it's a little challenging integral. It's integration by parts a few times. I would leave it to you. The final answer would be 4 square root of 2 times pi. So these are not easy integrals to do. So I just wanted to show you that how we can compute the volume under one of these surfaces which we saw before. So we had seen these surfaces, right? These kind of surfaces. We talked about these surfaces. This is a paraboloid. Using this new technique of integrals, we can compute the volume of these things, the volume under these surfaces. So that's pretty amazing. We can compute the volume of the regions, the solid regions bounded by these surfaces. That's the goal of this kind of integral. Okay, I wouldn't tell you more about that. That's quite a challenging thing. It takes a lot of time and practice to kind of master. Well, it's not, that's the problem. It's never really easy. This one was one of the, well, someone has asked if we can do something which is easier. It's never really easy. Let's continue. If we have time, we would come back. But so there are two things. One is that we should understand how to do it, like what is the volume. The other one is to be able to compute those integrals. I mean, those integrals might be a lot of integration by parts and those kind of things. Yeah, we can do another one. Let's try another one. Not with exponentials though. Suppose this easier thing. So suppose we have a sphere, right? X squared plus y squared plus z squared equals 1. This is a sphere with radius 1. Suppose I look at this semisphere and I want to compute this region, the volume of this region there. So it means I should think about that as a function of f of x and y. So it means let z to be equal to f of x and y. What would that be? Well, z squared is 1 minus x squared minus y squared. So z would be plus or minus square root of 1 minus x squared minus y squared. Therefore, we are taking the positive one. It would be square root of 1 minus x squared minus y squared. So I want to compute the volume of that thing. It should be double integral of f of x and y, which is 1 minus x squared minus y squared, dx, dy. What are the bounds for x? What are the bounds for y? Well, if I want to find the bounds for x or y, well, here first x. I should let that thing to be equal to 0. I can isolate x. X squared would be 1 minus y squared. X would be plus or minus square root of 1 minus y squared. So integral would be from 1 minus y squared, minus 1 from y squared to 1 minus y squared. What are the bounds for x? I should ignore y. I would get 1 minus x squared. I should let it to be 0. X squared would be 1. Therefore, x is plus minus 1. So this is the volume. Now, the second step is to compute this integral. And this is not really easy. I mean, I know how to compute this integral, but even in this very easy case, it's not very, very, very clean. So this would be the volume, but not, again, not easy to compute. I think I understand. Someone said exponential. I think I understand now. Actually, we can define a surface using exponential too. That might be easier. I would talk about spherical coordinates. Yeah. The previous one, actually, this is not very hard, actually. It's with the use of spherical coordinates. I would speak a little bit about that. So I might come back to this one. But before that, let me mention the other idea. Someone said maybe we can consider, maybe we can consider an exponential function. Let's think about that. F and xy would be something exponential. Let's say it's e to the x. So we can look at the graph of this function, but we should put bounds here. This is okay. This is not as natural as the other ones. We can look at the graph of this function, e to the x, z equals to e to the x. It's a surface. This surface would look like this. I'm not sure if it's very clear. It's a cylindrical surface. Okay, and suppose bounded by, okay, it's a little not very natural. I should give you the bounds. Bounded by, say, planes. Say this plane z equals 0. And then I should give you bounds for x, say x equals to 1. That would be this region. And then I should give you, maybe I can do it with another color. This is x equals to 1. And then I should give you bounds for values of y. Say y equals to 0 and y equals to 1. Maybe I can, let me see if I can try to, first of all, show you how this thing really looks like. So it means, do you see here we have like a box. I'm not sure if it's clear. We want to find the volume of what we have there, like inside that box. Does anyone, can you see, or if my drawing is really bad? Okay, let me see. Yeah, let me try to see if I can sketch it for you. Well, if you can see, that's pretty good. It shows you have good intuition, geometric intuition. But let me try to sketch it. Okay, so here our function z is e to the x, which looks like this, right? And then we have another one. We need another one, which is z equal to 0. This one, you see there are two of them now. And then we have another one, x equal to 1. That's one of them. We have another one, x equals to 0. That's another one. Now, or did we have that? I think we didn't have that. So I think what we had was y equals to, maybe I made a mistake. Yeah, y equal to 0 and y equal to 1. Thank you. So y equal to 0. That's y equal to 0. And then we have y equal to 1. So do you see these things? Well, they're intersect. There is some region there bounded by these things. So maybe I should continue these things a little more to see how they would really intersect at some point. I would later make, well, I would change the transparencies to see something. So maybe if I bring transparencies down, it might be easier to see what we are doing. Okay, it's really hard to see anyway, but you might be able to see there is a region, there is some region bounded between all these planes. Okay, it really didn't work as well as I thought. So there, as you can see, under this exponential surface, if we add some, it's like a house, right? If I add some roof and ceiling and the walls, there is a region bounded here, just like here, with two planes. That I'm interested in finding that region, the volume of that region. Let's go back. So I should compute the integral of f of x and y dx dy. So here f of x and y is e to the x dx dy. Well, I explicitly said I should decide about the values for x and the value. I mean, this is kind of artificial. Let's say x is between 0 and 1 and y is also between 0 and 1. Suppose this is given in the question. So I can take integral from 0 to 1. Maybe it was better if it was minus x or minus x squared, but anyway, it doesn't really matter. So integral of e to the x is, with respect to x, is again e to the x from 0 to 1. So it would be e minus e to the 0, which is 1. And then I should take integral with respect to y, which would be e times y minus y plus 1 to 0, which is e minus 1. That would be the volume of that region we just saw. Or maybe we really didn't see. But that's the volume of that region. So it's kind of like, so it's like we have this surface, exponential surface, and we are kind of bounding it from different directions with these planes, and then we get some volume there. That's what the volume is. anyway, even if we can't see it very well. Okay, so that's all I want to say about these triple integrals. Well, we didn't really do the triple integrals. We kind of, we prefer to go around it and use the double integral again to compute the volume. But that's how it is. So that's section 14.2. We did 14.2. Now we get to 14.3. I want to, it's interesting to mention because we talked about polar coordinates. So I want to just mention very briefly how we can use polar coordinates in order to compute integrals. Just through a few examples. So remember, in polar coordinates, so suppose we are in two-dimensional space. We have x and y. In polar coordinates, we use r and theta. X is equal to r cosine of theta. Y is equal to r sine of theta. And r squared is equal to x squared plus y squared, and tangent of theta is equal to y over x. These are the ways to go from polar coordinates to rectangular coordinates, or vice versa, to go from rectangular coordinates to polar coordinates. Okay. Now, sometimes when we want to find volume or area, writing things in terms of polar coordinates is pretty useful. Again, I would use one example of the book. Well, I would change it slightly, or maybe I would use it. That's a good example. So actually, this is a classic one. So suppose we have two circles, okay? Say there's one circle around the origin. There is another circle around the origin. We have two circles. One of them is, say, x squared plus y squared equals 1. The other one, well, let's say x squared plus y squared equals 4. So the radius of this one is 1. The radius of the second one is 2. Okay, we have two circles centered at the origin. Radius of one of them is 1. The radius of the other one is 2. And then we want to compute the integral of a function here, say x squared plus y dx dy above this, or this region, above this ring between these two circles. So let's call this red place R, above this place R. What does this thing mean? Okay, this is a notation. So when I write R here, it means I should use this geometric picture here, this ring between these two circles, to find the regions for x and y. So here the regions for x and y are not written explicitly. The idea is that I should be able to find them, okay? So how can I say what, so if I take a point here, it means I should say what are the bounds for x and y. But it's pretty challenging problem. Why? Well, look at this picture. Let's look at it more carefully. I have this circle here. I have another circle inside. I want to see what are the bounds for x and y for the points inside this ring, right? So suppose I have a point here. If I want to find the range for y, it means I should say what are the bounds for y. The y can be at max this thing, at min this thing, but not really. I mean, y can be something in this area too. If I take the point here, the bounds for y would be this area. Yeah, that is true. So if I take my point at different places, the bounds for y, it changes. Do you see? Here the bounds for y, there is this point and this point, they give the bounds for y. But if I choose the point here, y either should be between these two, or maybe y can be something above this thing. So it's pretty complicated. There is no way really to say what are the bounds for y, or the same thing holds for x. What are the bounds for x? There is a discontinuity there. You see there's a gap there suddenly. It seems y can be in this region, or it can be in this region. So it might get it might be in different 2 bounds. Or if the point is here, well, there's just one region. So it's a little strange. The idea is that if I go to polar coordinates, so if I'm in rectangular coordinates, I should tell you what are the bounds for x and y. If I go to polar coordinates, I should tell you what are the bounds for theta and r. Well, that's pretty simple. It's really simple to say what are the bounds for r and theta. What are the bounds for r? So we couldn't really say what are the bounds for x and y. But what are the bounds for r? The radius. It's very, very, very obvious. So we are going from this circle to the other circle. What are the bounds for the radius here? It goes from the small circle to bigger circle. Small circle has radius 1, bigger circle has radius 2. So it would be between 1 and 2. What are the bounds for theta? Well, theta can start here at 0. It can go around the circle. It comes back at 2 pi. So the bounds for a circle are 0 to 2 pi. Why 3? I'm not sure what you mean by 3. Okay, so if I write things in terms of r and theta, the bounds for r and theta are pretty clear. So that's what I'm going to do. So I have this integral x squared plus y dx dy. I should also introduce a notation. Sometimes people, rather than dx dy, they just write the a. So because maybe we don't want to write a lot, we just write the a. Sometimes instead of dx, dy, dz, they write dv. These are just notation. Kind of, you can think about it as abbreviation for now. Anyway, so here I have x squared plus y. What is x? X is r cosine of theta. So it would be r cosine of theta squared. Okay, I have 3, there are different questions I should reply. Maybe I should go back. Someone said why the radius is not, the big circle has radius 3. No, I mean the radius is the square root of this number here. The square root of 4 is 2. That's how we find the radius of a circle. We take square root of this number here. If you're still confused, tell me. Yeah, and then someone else said, why is x squared plus y not x squared plus y squared? That's the question. The question, so maybe I should tell you the question again. The question tells me, okay, maybe I wasn't pretty clear about the question, sorry. So the question, I would tell you the question one more time. The question tells me, consider this region between these 2 circles. We have 2 circles, x squared plus y squared equals 1, and x squared plus y squared equals 4. I'm a little sorry, I have not slept last night, unfortunately. That might be, these are the signs of not sleeping during the night. So we have 2 regions, we have 2 circles. It says consider the region between them. Let's show this region with r, okay? The question says find this integral, the double integral, x squared plus y dx dy over the region r. Now, I was telling you, what does this thing really mean? What does it mean to find? This is part of the question. So why it's not x squared plus y squared, it's x squared plus y. It's part of the question. The question says, find this integral of this function over the region R. Now I wanted to tell you, what does this thing really mean? What does it mean to find integral of a function over a region? It means, well, just like what we did before, we should take this integral, we should compute this integral, but we should know what are the bounds for x and y based on this region R. If this region R, this is the area, this is the region bounded by these two circles, I should find, this means find the bounds for x and find the bounds for y. So if I find the bounds for x, for example, say x goes from something to something else, if I find the bounds for y, if I write them here, I can compute this integral, and that would be the answer. Okay? But the problem is I cannot really compute the bounds for x and y here. It's not easy to find the bounds for x and y, because as I said, if you take a random point in this region, different things might happen. If you take your random point here, as you can see, the bounds for the y component of that would be, it's above this point, it's below this point. But if you take your random point here, if I want to say what are the bounds for that, it would be either it's in this area, in this region, or it's in this region. So it's really, the bounds really change, they change based on the point I take in a very strange way. And it's very hard to say what are the bounds for x and what are the bounds for y. But if I write everything in polar coordinates, things will become a lot easier. So remember, x is r cosine theta and y is r sine theta. Okay, does the question make sense now? Is it more clear what we are trying to do? Okay, that's good. So now we are taking integral of x squared, which is r cosine of theta squared plus r sine of theta. Okay, I should see what is dx and dy. Well, dx is, what is dx and what is dy? That's a very good question. Let me go to the next page. So x is r cosine of theta. What is dx? Well, it is d of r cosine theta. It kind of works like the, well, it is a product rule. D is kind of like taking the derivative. So it would be d of r times cosine of theta plus r times d of cosine of theta. Okay, so the first one says it's dr cosine of theta. The second one says it's r d of cosine of theta. But what is d of cosine of theta? I should take derivative of cosine, which is minus sine of theta, and then write d theta. So I would get dr cosine of theta minus r sine of theta d theta. On the other hand, y was equal to r sine of theta. So what is dy? It is d of, well, y is equal to r sine of theta. So it is equal to d of r. It is again product rule. It's d of r times sine of theta plus r times d of sine of theta. Okay, we have dr sine of theta plus r. What is d of sine of theta? I should first take the derivative of sine of theta, which is cosine of theta, and then multiply it by d theta. Now, these are dx and dy. When I do a change of variable, I should do change of variable in everything. So here I have a function x squared plus y dx dy. It's equal to, x squared is equal to r cosine of theta squared. Y is equal to r sine of theta. Instead of dx, I should write what I computed there. Instead of dy, I should write what I computed in the previous slide. So dx, and then I should multiply them. Dx and dy. Okay. So what was dx? Dx was dr cosine of theta minus r sine of theta d theta. What is dy? Dy was dr sine of theta plus r cosine of theta d theta. And we should kind of multiply them. The correct word for that is we should compute their wedge product, but it's okay. You don't need to know this word. So it would be dr cosine theta times dr sine theta plus dr cosine of theta times r cosine of theta d theta minus r sine of theta d theta dr sine of theta minus r sine theta d theta r cosine theta d theta. Okay, now I'm going to tell you one important rule. Whenever we have dr and when we have dr again, it is 0. When we have d theta and d theta again, it is also 0. So here, see, we have dr multiplied by dr, that's 0. You see here we have d theta multiplied with d theta, that's 0. That's kind of out of the scope of this course, really, to explain why that's the case. Let's just accept it at, the real reason is that they are examples of what is known as differential form. And differential form, their multiplication is not commutative. So if you have dr d theta or whatever, if we change their order, it becomes negative. So if I have dr and dr, if I change their order, so if I write this dr first and the other dr second, it becomes negative. But how can dr be minus dr? Well, if I take this one to the other side, it means 2 dr is 0, which means dr is 0. That really doesn't matter for us very much now. It's not something we should really talk about. It's a little bit more advanced than this course, but that's the case here. So what are the things which remain? Well, we have here r cosine theta times cosine theta, which is cosine theta squared, dr d theta. What about here? Here we have r sine theta, which is sine theta squared, d theta dr. So here we have d theta dr. I want to change their order. So if I change their order, it becomes negative. So there's minus here, there's another minus here, it becomes plus dr d theta. Now, if I add these two, I would get r times cosine theta squared plus sine theta squared dr d theta. But cosine squared plus sine squared is 1. So I would get r dr d theta. So a lot of times in the books, you might see they don't explain this thing. They might just say as a rule, dx dy is r dr d theta. You can simply memorize that without going to these details, but this is kind of the proof. Okay, so I have this function x squared plus y dx dy. I should take its integral. It would become double integral of r cosine theta squared plus r sine theta. The whole thing times r dr d theta, which is equal to r cubed cosine theta squared plus r squared sine theta dr d theta. What are the bounds for r? We are looking at this region between these two circles. We go from the circle with radius 1 to circle with radius 2. So the bounds for r is 1 from 2 to 2. What are the bounds for pi? We go from 0 to 2 pi. We go all around the circle. So it's 0 to 2 pi. And we should compute this integral. So I should compute the integral with respect to r. So I should first compute this integral. So I would assume theta is a constant. I should take integral with respect to r. It would be r to the 4 over 4. I take integral with respect to r. I should put these values in that. I would end up with 6 cosine squared of theta plus then it would be, or it would be 8, sorry. 8. So it would be 8 cosine squared theta plus 4 sine of theta. Again, there is not really enough space. Maybe I should go to the second page, or I can just write it here. It's okay. Okay, so I would get cosine squared of theta times 16 over 4, which is 4. So 4 cosine squared plus 8 over 3 sine squared minus 1 over 4 cosine squared minus 1 over 3 sine theta. So that would be the result of this thing. And then we should take another integral with respect to theta. Again, I wouldn't do that. These integrals actually take a lot of time. If I want to do each of them, probably we wouldn't get to the next topics. But the idea here is that we should take integral of things like sine squared, cosine squared, and integral of sine and cosine. The idea of how you can take integral of sine squared and cosine squared with the use of this thing. So if you remember, so for example, if you want to compute integral of cosine squared of theta, just as a point, you should remember that cosine of 2 theta is equal to 2 cosine squared of theta minus 1. Therefore, cosine squared of theta is equal to cosine of 2 theta plus 1 over 2. So cosine squared is equal to cosine of 2 theta plus 1 over 2. You should use this formula to compute the integral. I wouldn't say more about that because this goes back to change of variable, and sometimes you should do integration by part and things like that. Yeah, but that's how we compute these integrals and how the polar coordinates helps us to compute that. Okay, that's it. I don't want to specifically talk about polar coordinates more than this. Chapter 14.4 is about 2 things which I'm really interested in them, but I don't think we would talk about them. One of them is center of mass and moments of inertia. So I told you you can read parts of the book and teach it or explain it to other people. For example, center of mass can be one of them. We understand center of mass one way in our daily life. Maybe if we know it's mathematics, we would understand it in another way. So one of those extra credit things, you can think about this section, 14.4. Okay. There is one more thing I want to speak about, and that's 14.5. Maybe it's good to have a short break. Do you need break, or you think we can continue? Let's see. It's 11:15. We have time. Probably we can. Oh, continue. That's good. We would continue. That's amazing. So let's continue.